欢迎收看本期的 I Can X Story 大师故事，我是主持人王慧。在这里，我们遇见大师，分享智慧，让科学成为我们共同的故事。今天我们非常荣幸邀请到了纳米材料领域著名的科学家，美国莱斯大学材料科学与纳米工程系创始人 Pulickal Ajayan 教授。16000、1200、190。这些看似毫无关联的数字，对于Ajayan教授来说，却有着特别的含义。16000是他文章的总被引次数，1200是他发表的期刊论文总量，190是Ajayan教授的 H 因子。这一串惊人的数字，足以让任何一位学术同行起立鼓掌。作为著作等身的科学家，Ajayan教授不仅发文量巨大，而且他发文的期刊也都是国际顶级学术期刊，如 Science、Nature、PNAS 等等。那么他是如何写出这么多优秀的学术论文呢？今天他将在节目中分享他的独家秘籍。作为享誉世界的科学家，Ajayan教授更是获奖专业户。英国皇家化学学会斯皮尔斯纪念奖，美国 MRS 金奖，德国资深洪堡特奖和休斯顿中心颁发的终身纳米技术奖等诸多奖项都被他收入囊中。今天他也将在节目中分享他对获奖的心得体会。作为一位长期活跃在学术最前沿的科学家，Ajayan教授的研究工作涵盖纳米材料从原理、加工到应用的诸多领域，从纳米颗粒、纳米管、二维材料、纳米复合材料到石墨烯等等，他是名副其实的纳米技术领域先驱。今天他也将在节目中分享他对科学方向选择和把握的心路历程。现在让我们一起走进 I Can X Story， 来听听Ajayan教授的故事。
So hello, Professor.
Hello, hi.
It is really my great honor and pleasure to have this interview with you. Thank you for accepting the invitation.
Thank you.
So your research covers a wide field of topics, including carbon nanotubes, 2D materials, nanostructured materials, and composite materials, etc. So can you briefly introduce the current research focus of your team and its future development prospects?
We are basically material scientists, and my group has always looked at developing platforms using nanomaterials. So the application for us is not that key, but essentially looking fundamental, the basic science of materials, assemblies, and nano engineering is our interest. So as you said, for a very long time, we have looked at all kinds of nanomaterials, starting with carbon nanotubes and later on getting into graphene and then coming into 2D materials. We have looked at inorganic nanoparticles, polymer-based nanocomposites. So a wide range of materials we have looked at always. And the real excitement for us is to see what are the opportunities and what are the challenges when you start to nano-engineer structures to larger scales. So, if you have, for example, carbon nanotubes and you're trying to assemble them into a fiber, what is a bottleneck? What is the challenge? And how do you most effectively engineer these structures so that they could be useful in applications? It's the same story for, let's say, graphene as well. How do you make a very large area graphene layer with the right kind of properties so that it can be useful in practical applications? Or 2D materials. How do you create some stacks of 2D materials that has some emerging new behavior? They call it van der Waals, artificially stacked van der Waals structures. Or maybe how do you take each layer and create these twists so that there are some emergent and exciting physics in these systems. So it's always talking about or thinking about how you can take these building blocks and how you build platforms so that they could be useful for applications. Again, when you really go into applications, you have to build larger structures, you have to build 3D systems. And how do you accomplish this from low-dimensional building blocks? So that's always been our interest. How do you look at interfaces, and how does the interface affect the overall property of the system? So in that perspective, we look at many applications, and we have worked on many applications over the years. We look at energy storage, for example. We work on batteries. We work on supercapacitors. We work on electronics and sensors. That's another area to utilize some of these nanostructures. We work on additive manufacturing, 3D printing. How do you actually build from bottom up to create interesting structures, and how does the mechanical properties affect this structure property correlations? How do you create the right kind of geometries so that you can create very fascinating mechanical response? So there's a broad range of things we do and we have done over the years, but it's always about nano engineering and engineering nanomaterials to specific functions. So that's kind of a broad answer, but again, bottom line is that we are very much focused on fundamental science and basic science. Applications are essentially our targets, long-term goals, but we are very interested in looking at the fundamental properties of these materials.
Over the past 2 decades, there have been real innovations and amazing discoveries in the nanotechnology. And just as you mentioned, however, there are still challenges in engineering of the nanomaterials and the integration of materials into application and the commercial products. So when facing such kind of challenges, how do you adjust yourself, your psychology, to solve the problem?
In my mind, there are 2 types of problems or challenges. One is intrinsic to the materials and intrinsic to the structure and the systems that we look at. And then there are the extrinsic problems that are related to scalability and cost and other things. Let me say a few things about the intrinsic issues. And intrinsic, what I mean is that the challenges related to the fundamental properties of the material and the fundamental issues in going from small scale to large scale. So if you look at the very basic problem that I face is that it's extremely difficult in the area of nanomaterials to have size specific, size selected, structure specific, structure selected creation of these building blocks. The nanotube area is a great example. We have been working on nanotubes for the last, since 1990s, early 1990s, almost 30 years. Still it is really challenging to get to one specific dimension or one specific chirality. And I think this problem is intrinsic to nanotechnology in general. It is not just about nanotubes, but the nanoparticles have the same issue. Can you create clusters that have a large number of clusters, huge volumes of these materials that have very same structure, size, dimensions? So that's one of the fundamental problems.
Hi, Mei
So
Qi.
how do you solve that problem? I mean, I don't think people have really thought about this in a great detail. I think people are interested in looking at nanostructures, finding their exciting properties, and then proposing an extension of that to the real world applications. And that's not always the case, right? And another intrinsic problem that we face is when we start to build interfaces. Right? Interfaces are key in many of the nano-engineered, nanostructured materials. And it's very, very difficult to control interfaces. Let me again take the example of carbon nanotubes. A single nanotube is really an amazing structure. It is probably one of the most perfect, one of the most exciting material with huge amount of explored properties. Mechanical properties are amazing, the highest modulus, I mean, all kinds of things. But the problem arises when you start putting things together, let's say to make a fiber. Why is it that today, even after 30 years of work, we cannot get a super fiber from nanotubes? It's because of the interfaces. How do you manage the interface? How do you really connect these things together? And because they are very small, you have to find generic approaches that would allow massive interface engineering. And it's extremely difficult. So on the one hand, these nanostructures might offer exciting properties at the very atomic scale or at the slightly larger nanoscale. But as you build up scale, you find challenges. Of course, there are other problems. I just gave you a couple of examples. There are problems, for example, interfacing two different types of materials. For example, let's say nanotube is a great semiconductor material, or graphene or 2D materials are great in electronics. But the moment you start putting contacts, then the problems becomes different, right? Then everything is dictated by the interface between the metal and the semiconductor. And how do you engineer things at the very small scale is also a very difficult problem. So although these materials have amazing properties and amazing way to tailor their properties, finally, speaking, the transition from these individual building blocks to the larger scale structures that we really are interested in terms of applications becomes quite difficult. Of course, things like cost. Of course, everybody, the material that would compete and win will always have cost efficiency. So, I just give you a few examples, both intrinsic and extrinsic. The reason why nanotechnology has really become, as big as it was expected many years ago is because of these problems.
And as you are one of the pioneers in the field of carbon nanotubes and have participated in the early work of this field with the NEC team. So what inspired your research?
That was the golden time of nanotechnology because it was just beginning to happen. I still remember I met Professor Ijima when I was a student at Northwestern, and he came and gave a talk. And we were both working in somewhat similar fields. We were both microscopists. We were working on small particles and phase transitions and things like that. So his talk really, got me excited, and I asked him if I can go to Japan, and he said yes. And then, I joined in 1990, and the nanotubes discovery, you can see it, came out just a year or so after that. I think it was fascinating times because everybody was looking for something related to nano. The fullerenes were just discovered. In fact, fullerenes was discovered at Rice. That's the other connection that I have now, because I'm at Rice. The fullerenes were discovered. The people were getting better at making clusters of different materials, and lots of predictions and theory were just beginning to happen to see how exciting this whole field will be. Yeah. So it was that perspective that really that got us going. And there were many people at NEC trying to find new types of structures, analogs of fullerenes. The Professor Jima and his team just stumbled upon this fibrous-looking carbon material that was different from fullerenes. Although most of the focus was on fullerene research at that time, this new analog, this new structure that came out from microscopy really gave a different perspective. And there was some theoretical predictions that came right afterwards saying that, you could have this chirality, which will influence electronic properties. So there was this real, new avenue that opened up that people can really explore. So that, in that sense, it was extremely exciting. And of course, when you find a new material, there are many other things as well. How do you make it the yield better? How do you make the synthesis process better? So we were looking at many different directions, and some of them were actually serendipity. For example, we published a paper, myself and Professor Jima, in 1993, early 93, in Nature, of filling of carbon nanotubes. Again, nobody really expected it, so it was kind of a surprise. Mm-hmm. But the fact that these cavities inside nanotubes are so tiny, and it could actually suck some material inside, opened another door, right? So that you can make these hybrid heterostructure of nanomaterials and study them. So, especially when you're in early in a field, there are many things that opens up, and you kind of go in different directions, and everything that you find becomes exciting. So great golden time, as I say.
Yeah, great. And you are a member of advisory editorial board of several materials science and nanotechnology journals, and a member of the board of directors of several nanotechnology companies. Do all these positions contribute to your research?
So, I mean, as part of the academic world, you do many things, right? I mean, you do research, you do service, you do teaching. I mean, they're all important, right? And they all contribute to each other.
Yes.
Education is a good example. I mean, whenever you teach, your research is also part of that teaching process. So, I think it's a symbiotic relationship between research, teaching, and service. And as you said, you being a part of the advisory board and journals helps you to see what is new and what is happening. It keeps you very current in your business. Or if you are part of some companies, you get a different perspective. You see that, what kind of materials that you build are getting translated into real applications. So I think it's very important for people to have different perspectives and merge them in the work that you do. So, being in all these committees and boards and stuff like that certainly has helped, shape my vision for our own research. And, of course, this doesn't happen early in your career. As you get more senior, you get drawn into many of these things. Of course, not every one of them is as useful as you can possibly think. Service is part of what we do as well. I think reaching out to the bigger community is very important.
Yeah, and with multiple jobs, so how do you manage your time?
So time management is the most difficult problem, right? I mean, I think I'm not sure if I manage my time very well. I mean, that's hard to really tell. But with time, you kind of get a sense of what is really important and what you need to prioritize. And prioritizing is probably most important thing. I mean, for example, I'm a professor. I have to teach. I am a department chair, so I have to have administrative duties for the department. And of course, you have to run a big group of researchers. So, you don't really micromanage, because micromanaging would take all your time. So you need to figure out the right balance in terms of engaging with the different constituencies when you're doing these multiple tasks.
Great. And you have been awarded many heavyweight awards, such as the Houston Technology Center Lifetime Achievement Nanotechnology Award, the Senior Humboldt Prize, the 2006 MRS Medal, and the RPI Senior Research Award, etc. So what is the secret of your success?
Well, I mean, awards are really not that important. And honestly, I've never really thought that, that's what is driving my career. What I really like is to have conversations with my students and brainstorming new ideas. And the pleasure you get from that, you don't get anywhere else. Right? So, yes, I mean, it's important that people recognize those who have contributed to different fields. But that's certainly not the most important thing. And I think everybody should, at least most people should realize that. And with time, you do realize that. I think we all understand that science is a cumulative effort, right? What we have done is that we have built on what others have done, and the next generation will build on what we do. And I think that's the important link. Recognition. Yes, I think it's part of our culture and part of our society, but putting too much emphasis on that, I think we kind of get diverted. And that's, again, I mean, of course, I'm happy that, I get some awards and, people recognize me. But I think, they should recognize for the work that you do, right? And that's most important. And that's the one that will stay for a very long period of time.
Thank you. So, how do you deal with difficulties and the bottlenecks in the process of scientific research?
Yeah, so that's again a very important question, right? And I think everyone who is in research should be asking that question. So again, there are intrinsic challenges and extrinsic challenges, right? Intrinsic challenges is when you are struggling with problems, and you find it kind of hard to progress in the research that you do. Of course, research and science is a very logical thing, and you have set protocols and you have set procedures to do things. But you could end up in a situation where you're not seeing light at the end of the tunnel, and you could be stuck in certain, what I want to call local minima, right? And that's that's frustrating more than anything else. And I think to have patience is very important, to have the realization that not everything is going to be as exciting, everything that you do. So there are things that you have to do that that essentially fill space. But of course, as part of this, there could also be a lot of exciting things that come along. But then there are also extrinsic or external factors that make things difficult. For example, having funding for the research that you do, right? I mean, that's a big challenge, particularly if you have a big group. How do you generate resources and facilities and infrastructure that keeps us really at the top of the business? And that to sustain this for a very long time, it's probably very difficult. Of course, it changes from country to country and place to place. But in general, I think people who have done well are people who have constantly struggled and strived to get resources for their research programs, and that's it's a continuous, oftentimes difficult thing to manage.
You have been invited to give hundreds of speeches in more than 20 countries. What suggestions would you give young colleagues who are hoping to deliver a good report or wonderful speech?
That's again, we have this talk all the time in our group meetings. So I think what my message would be that start early. Especially when you're in a research group, volunteer to maybe give talks in the group and stuff like that. At the end of the day, focus on a few things like clarity, and again, the kind of content that you would talk about. Keep excellence as your real standards, right? I mean, every time you do something, make sure that is perfect. At least in my mind, that's one of the things that makes you do well. But even things like the content that you use is important, right? It depends on the audience. In fact, the question that I asked, who is the audience, is very, very important.
Yes.
You can give the same talk in 10 different ways to 10 different audiences. So it's very important to take into account who is listening to you and what they are looking for.
Yes.
And it will be, that's a good message, I think, for youngsters.
Yeah. Yeah, I totally agree. And as you have published more than 1,000 papers in many kinds of top academic journals, such as Science, Nature, and PNAS, etc. So could you tell the students how to write good papers?
Yeah, I mean, it's a learning process, right? I mean, the first paper you write is not going to be the best in your career, so don't worry too much about it. But I think for those kind of high-end journals, I think content is important. Of course, they're not going to publish something that is not novel or unique or exciting. But that's not the only thing. I mean, you could have an exciting result, and you may not be able to publish in those journals.
Yes.
So, take the content, think about the right story you want to write, think about the right things that you want to convey in that paper. So it's again a balance that you will strike after several trials, and don't give up. I think that's the most important thing. Many of the people who publish in all these journals don't think that they get everything that they send out accepted. They also have the same kind of success rate, perhaps. But you keep trying, and you don't lose hope, and you focus on importance of your work.
Can you list a few names that have a major impact on your life and your scientific research, and why?
Well, I mean, most of us are in science or engineering because there were some teachers in our schools or colleges who were outstanding, right? I mean, those are my heroes because, I got inspiration from many professors in my undergraduate times to think that, this is the greatest profession that you can ever have. This is the greatest thing that you can ever be in, research and science. And so, of course, there are these bigger than life figures, of course, like Einstein and people like that who always impress you. And, for example, they're all characters that you can always look up to, right? But I think the real inspiration comes from those people who have taught you and who have really been part of your early career. I still, consider that I have been very lucky in being able to be part of many, many outstanding professors and, teachers. And in life, I don't know, maybe one name that I might just say, who I'm always thinking about is maybe Buddha or somebody like that, right? Who at the height of his life just decided to give up everything and just go away and think about something else. Human beings are, we exist because we can think and, we can talk to ourselves and others, right? And that thinking process is most important. And yes. I think people who has really thought differently at any point of their life are who actually fascinates me.
You have been engaged in carbon nanomaterial research for so many years, and what suggestions do you give for the young students? Yeah.
Well, carbon is a fascinating element, right? You have carbon in everything. And, even from a solid state carbon perspective, I think there are lots of things that are happening. And I think a lot remains to be explored. We have already seen things like nanotube and graphene and diamond-based materials. There is much more, I believe. Doped carbons, for example, highly porous carbons. Carbon fibers is going to be a major industrial commodity in the future. It's already there, but it will be much bigger, I believe. So even from a purely a single element material point of view, I think carbon is enough for a lifetime, right? So we still work on carbon. It's amazing. After 35 years. And but again, that's probably true with lots of materials that people work on. But I have worked most of my life on carbon, and I have a special taste for carbon, I suppose.
So thank you very much. Thank you for your time.
Thank you. Thank you. It was really nice talking to you.
感谢Ajayan教授的精彩分享，相信您听完这期访谈，也会对他的精彩人生和科研产生了非常浓厚的兴趣吧。那么他研究的到底是什么呢？其实说起来，您也许很熟悉，就是我们常说的神奇的、肉眼不可见的微观世界。这个微到底有多微呢？如果可以用微米来形容，1微米是1米的10的负6次方分之1，是我们头发丝直径的1/100，而1纳米是1微米的1/1000，1纳米相当于4倍原子的大小。Ajayan教授就是这微观世界的建筑师，他以原子为砖，分子为靶，以纳米为尺，以微米为柱，为我们建造了一栋又一栋神奇的微观建筑。如果您也对微纳尺度下的神奇材料感兴趣，想了解2维原子层结构，想知道最近纳米材料领域有哪些令人激动的发现和未来潜在的应用，请锁定 iCanX Talks， 听一听Ajayan教授关于纳米工程材料的精彩报告。 遇见大师，分享智慧，让科学成为我们共同的故事。我是主持人王慧，我们下周再见。
Hello everyone, this is Alice in Beijing. I'm so glad to meet you again on ICANX Talks. Actually, we met every Friday at this moment to 8 o'clock in the evening of Beijing and 8 o'clock in the morning of New York. So ICANX Talks was a long-term, program, online talks. And now we start this week's session. I'm the moderator this week. Hi, Xiazhang. My English name was Alice. I think many of you already know me on this program and on this platform. So yeah, this week is really the first week of our June program. And June 4 week, we will have 4 wonderful speakers. Today we'll get on the stage is Professor Ajayan from Rice University. And next week, we will have the Nobel laureate session with Professor Lien from France. And then after, we will have the speaker from Europe too, as Stephanie Lecoux was from EPFL, Switzerland. And then afterwards, the last week of June, we will have Professor Yanyi Huang, was from Peking University, the same university as where I am. So this was our June's program. Today is the first day for the June, the week we have. And so this we will have also in this stage we have our super challengers. We name them as X challengers because as every week we invited one young scientist. They are either postdoc, they are either the young AP assistant professors. So they will get on stage to ask some challenging questions to the senior scientists. So we have 4 of them will get on the stage and every week, so you will see them soon. And today is Maggie, so you will see Maggie in 1 hour. So this week, yeah, as I say, was the first week of June. We have the very big name in nanotechnology with Professor Ajayan, and we have this team, on the stage tonight with me was Nick Fang from MIT as our panelist, and X Challengers Meiqi, was from Peking University. So this was tonight the program. First, we will have our speaker, Professor Ajayan. As if you're working in the nano field, you will never miss this name. Professor Ajayan was working in nano field since very beginning. I think it's about 30 or over 30 years ago. And he published 1,200 papers. So you couldn't miss his papers too. So I really covered a lot of field in this, nano engineering, nanomaterials, and also applications, many different areas. So tonight he's going to talk about, the challenges and the opportunities in this nano engineering field. So Professor Ajayan, the stage is yours, the word is yours, please.
You can hear me, right?
Yes.
Okay. Well, good morning from Houston. I hope everyone is doing well. As we all know, the last year has been pretty challenging for all of us, but technology has enabled us to do things like this, online talks and so on, and I'm so happy to be here. Thank you, Alice, for introducing me. We have been working on material science for quite a long time, and particularly focused on nanomaterials. I had my early career in carbon-based nanomaterials, and we have moved on to look at different structures like two-dimensional materials. So today, my talk is going to be more of a perspective from our end in the challenges in looking at some of these materials, particularly going from the building blocks to engineered structures. And in some sense, it's going to be more philosophical in the way that you evolve a perspective after working with so many different systems and find out what the real intrinsic challenges are compared to some of the extrinsic factors that ultimately will decide whether nanotechnology will have the impact that we have all been talking about. So let me show one slide that kind of tells you what this field is all about, particularly from the nano engineering perspective. You have all these building blocks, you have all these pieces that one needs to put together. And the field is defined essentially by the challenge in being able to do that. And to make, of course, matters very difficult, these pieces are invisible, they are in the nanoscale. And the question really is, what are the possibilities of building larger structures, which ultimately you want to be able to make them functional by putting these pieces together. And of course, there are some other challenges as well, because almost all the time you end up with looking at multiple compositions and multiple structures, and these interactions and interfaces become the bottleneck in the end. So today's talk is going to be many, many examples taken from almost 2 decades of work in my group to essentially present this whole platform on how you can deal with building structures from nanoscale building blocks. So it's somewhat a Lego approach, and that's essentially the focus of this talk. Now, the question is really, how do you go about doing this? There's been significant amount of work in the last few years in trying to build individual building blocks and understanding their properties. You go to the next level where you start to put things together. The question really is, how do you create these architectures? Because there are 2 broadly defined approaches. One is called the bottom-up approach, and the other one is called top-down. I will not talk too much about top-down, but we all know that platforms like electronics have done an amazing job of going down to the nanoscale using top-down approach. And top-down essentially means machining down lithography approaches. And today's microelectronics or nanoelectronics platform can work in the 10 nanometer regime, and they're even thinking of going down scale. So I will kind of let that aside, although I do believe that that is an important approach to build nanoscale devices and structures. And I will mostly talk about the bottom-up approach, which is the other direction of building nano-engineered materials. And there are many examples, for example, in nature, that allows one to look and see how this can be done. And these 2 approaches are quite different in many ways. The kind of structures you end up with are different. The scale at which you can do these things are quite different. And the final impact of these could be also quite different in terms of how small a scale you can go to and so on. So in my talk today, it's going to be mostly about how do you shape the bottom-up approaches and where we are today, and what kind of challenges we face, and what opportunities are there in this particular. As an example, let me just show this beautiful structure that many of us can have seen and are familiar with. This is really an exquisite example of these kind of nano engineering from the bottom-up approach. And this is done through complex mineralization approaches that nature has taken and evolved over many years, many millions of years. And what you see here is actually a spectacular example of a material, which is essentially calcium carbonate, a very brittle material, But when it is nano-engineered, packaged into nanoscale platelets of calcium carbonate and very thin layers of protein, provides you with an amazingly tough, mechanically tough material. So if you look at this, you wonder, how nature has evolved to appreciate this whole nano engineering. But obviously, evolution is a long and tedious and trial and error method, and it has kind of optimized these type of structures in order to survive, in order to be most efficient. And these are essentially good examples for us to emulate, although, the actual, practically, it could be quite challenging. So let me use this as kind of an inspiration in trying to build nanoscale or nano-engineered structures from these building blocks that I'm going to. So if I look at materials, particularly I'm going to show several examples of carbon nanotubes, which are, again, I started off working in this area very early on in my career. Then we'll come to another type of very different dimensionality material, 2D structures. But if you look at something like carbon nanotubes, what is really our ultimate goal if you were to build larger scale architectures from these building blocks like nanotubes? What you're seeing is a schematic, a theoretical design of a beautiful periodic structure using nanotube. You have a large number of nanotubes that are interconnected through covalent bonding, and you end up with a structure that could be quite fascinating from a mechanical point of view, maybe from an electrochemical point of view. And there are many, many such predicted structures that people have shown over the years. And even though it is pure carbon, graphitic carbon, if you design all these different complex geometries, it has been predicted that they could have really very, very different electrical, thermal, electronic properties. Some of them are very, very conducting, some of them are semiconducting. And the question really is, predicted structures look very good, but can you practically make any of these things? These could be perhaps the next generation of carbon materials that we want to really build. But from a practical point of view, is it even feasible to create these structures from a synthetic point of view? So that's one example. I mean, we have seen many such predictions, but very little experimental evidence that these could be actually created. Now, it probably depends on the scale that you're talking about. You could, in fact, create all these beautiful structures at a much larger scale using approaches like 3D printing. 3D printing is an additive technique, and it would be kind of the macro scale analog of bottom-up materials building. So in our lab, we have actually created all these shapes and geometries of these type of structures that I showed before, predicted for carbon, using 3D printing of polymer structures. And of course, these are, depending on the geometry that you build, there are many interesting properties that come out, stress distribution and stress concentration. All these things could be explored in these complex geometries. But of course, the problem is that when you go to the nanoscale, these are still not possible because 3D printing or additive manufacturing does not provide you the resolution that you require to build these at the nanoscale. So that's really the big question. So if you are not able to do this using scalable or continuous approaches like 3D printing, what other options do you have? So again, that's going to be the summary of my talk. And I believe that there are many factors that you can use to kind of think about creating three-dimensional structures from these type of building blocks. And it involves ideas of self-assembly, directed assembly, using chemistry, interfacial chemistry to kind of connect things. And of course, other materials processing techniques that would allow you to play with the lattice and the geometries of structures that you want to create. So let me kind of go into the practical aspects of some of these three-dimensional structure building from nanoscale building blocks. So when we were looking at nanotubes, many years ago, in order to create these larger area or larger volume structures, one of the options we had was to be able to assemble them in vapor phase. So, and again, not just us, but many other groups have over the years done a lot of work in vapor deposition, chemical vapor deposition using catalysts to create assemblies of carbon nanotubes. And I call it pseudo 3D structures because there are no real interconnections between the nanotubes, and they are almost van der Waals assembly. The nanotubes are simply aligned with respect to each other, and they don't have real three-dimensional interconnections. And these kind of structures, these films, or maybe in some sense pseudo 3D structures, have been extremely useful in many aspects. People have created supercapacitor devices using them. There's been membranes built from such interesting van der Waals assemblies. We have shown that they are highly absorbing light absorbers. So although they are not really 3D structures, there could be several applications that relate to these type of assemblies. And that's probably the step one in terms of building three-dimensional structures from nanoscale objects. Of course, the kind of vertically aligned nanotube films that I showed you are also not very homogeneous. They are made of nanotubes of different chirality, nanotubes have different dimensions. So in order to come to a more precision platform, we need to do a lot more processing. So here is another example of a film of nanotubes, but assembled in a very different way. So instead of this vertical assembly that I showed you in my last slide, here is an extremely aligned structure where all the nanotubes are aligned in horizontal mapping. And of course, this undergoes a lot of different processing steps. What this particular work, this was actually done at Rice and by Jun Kono's group. Essentially, what they did was to separate nanotubes based on chirality, and then you assemble them in this super aligned film modality. And this is the kind of structure that you ultimately want to build because this film has one type of nanotubes all aligned in one direction, and it kind of creates some amazing properties, particularly for light polarization and so on. And they have shown many different aspects of these type of films that are very well aligned. So again, to go from individual nanotubes that are manufactured in a rather random manner with different chiralities and dimensions and so on, to a film like this, it takes a lot of processing. And the question really is, how well you can optimize some of these processes so that it could be useful, and how scalable these films are. Now, going from this pseudo alignment where the individual structures are interacting through weak van der Waals forces, the question is, what is the next level of assembly? And that would be creation of 3D or real 3D nanostructures where the individual structures are interconnected. And of course, ultimately, you want to reach that highly periodic structure that I showed you at the beginning. But in the intermediate, most of the structures we can make today in the lab are not very periodic. They are kind of random interconnected structures, porous, low density structures of these type of materials. And we had to do some tricks here when we were depositing using vapor phase deposition. There are methods where you can introduce dopants, for example, boron, that would allow the formation of interconnections and so on. So you could get these type of three-dimensional interconnected structures from carbon nanotubes using vapor deposition. And there's also the other aspect where you can make these structures using chemistry. whether it is a nanotube or whether it is a graphene platelet. There are ways of interconnecting these using interfacial chemistry, functionalization, and then you can create larger structures from these building blocks, ultimately leading to really bulk material that have these building blocks of graphene. And again, the reason why one would do this is to be able to find applications. This particular structure was used for electrodes in batteries. One could think about these for gas absorption. So there are many potential applications if you can make these large-scale three-dimensional networks of nanostructures of carbon. It was also shown that structures, if it is properly interconnected, can have some very fascinating properties. So here is an example that shows the thermoelasticity in some of these interconnected structures. It was shown that if you can get graphene layers that are interconnected into 3D objects, they can show remarkable thermoelasticity. They are extremely elastic from a very, very low temperature, almost cryogenic temperatures, to very, very high temperature, close to 1,000 degrees. So I think if you are able to do this in a scalable fashion, you can create materials that have extreme properties. And that is, again, one of the reasons why we would build these 3D structures from nanoscale building blocks. And once again, the bottom-up approach of building three-dimensional structures allows you various aspects that are not possible from a top-down approach. You have flexibility, you can create hierarchies, you can introduce multiple materials at different stages of such assembly. So there are certainly advantages of the bottom-up. Now, interfacial chemistry becomes very important as well. This is an interesting example where we functionalized carbon nanotubes and then took them and brought them together through mechanical force or even grinding. And we were able to show that these functional groups that are attached to these, the surfaces of these nanostructures can interact and create reactions. So this is actually a condensation reaction where the functional groups that are attached to the nanoscale surfaces undergo interlinking and reactions that produces very, very fascinating reactions. So I think, again, the goal is to see how the chemistry that can be activated on nanoscale surfaces, and when they're brought together, can be utilized to specifically produce reactions, for example, catalysis and so on. So this interfacial chemistry has been utilized by many folks. This is not from our group, but it's from friends in IIT Chennai, showing that today you could build very large-scale cluster assemblies by the utilization of very size-specific clusters, for example, atoms, and these organic ligands. So in some sense, this kind of represents the future of this assemblies that I was talking about. How do you get the same type of nanostructure, inorganic nanostructure, whether it is these clusters of certain number of atoms or nanotubes of certain chirality and dimension, and how do you assemble them on a large scale? Right? In this particular case, they use organic ligands, and that leads to these kind of porous structures, and they can control the ligand sizes and so on, so that you can create different types of packing and different type of crystal structures. So again, what I'm trying to say is that the long-term goal for us is to build these periodic structures that I started with in the schematic that I showed you. In some of the kind of systems like molecular clusters, we are able to do that to a large extent. Still, as you scale to larger and larger scales, you start seeing a lot of defects and other issues. But for materials like carbon nanostructures, even this assembly is quite challenging. probably the best you could get is these aligned films and so on. And even those are not really interconnected in a three-dimensional way. So I think in terms of going from individual building blocks to larger scales of these nano-engineered structures, we still struggle, and we are still in the early stages of effectively building these architectures. And then there are also bulk structures that we are very interested in, like composite materials. And even this field has been quite challenging because dispersion of nanomaterials into a matrix has been really a difficult problem. Partly because of viscosity issues and processing issues, but also how do you really build the right kind of interfaces so that there can be a crosstalk between the matrix and the filler, whether it is carbon nanotube, whether it is a metal particle. This interfacial engineering, getting the right kind of interface in terms of molecular interactions is important in order to get good load transfer in a mechanically interested composite, or conductivity threshold or percolation in a different type of composite. So again, many of these kind of materials that we have always looked forward to building from nanomaterials, we have had limited success simply because of the difficulty in engineering them and the complexity of that interface that you end up creating. One could also think about complex building blocks. For example, we have done a lot of work, and many others have also done work in this templating approach. Going from simple carbon-based nanostructures to other multi-component systems. One can think about materials that could be quite fascinating. So here is a structure that is made of metal and carbon in the nanowire format. And what you're seeing is some kind of an assembly, depending on how these structures are created and assembled. So depending on what medium you put these in, they could assemble either with the gold or metal part facing outside or the carbon facing outside, and they could be reconfigured. So once again, a long-term perspective in nanomaterial assembly is that how do you create the right kind of building blocks that allows you to assemble and deassemble and so on. And again, with molecular clusters, this might be a much easier proposition, but as you increase and the complexity and the dimensions of some of these nanostructures, this is quite complicated. And this templating approach also allows you to put multiple components into the same nanowire system. So we have also done some work where an entire battery structure was created within a nanowire, and you can show that they can be fully functional batteries. Again, many of these engineering approaches depend on the system that you want to look at. Not all materials are possible, but there are ways of creating at least select systems into these type of nano-engineered formats and this. So just kind of finishing up the first part of my talk, which is mostly dealt with materials like carbon nanotubes and how they can be built into pseudo 3D or 3D structures. I want to kind of state that the real holy grail from a materials perspective in nanotechnology is a challenge of building three-dimensional architectures from nanoscale building blocks in controllable and scalable manner, particularly via the bottom-up approach. So let me now get into a very different type of materials and the kind of challenges that these type of structures face as you build up. And again, there's been a large number of works that has come out in the area of 2D atomically thin materials, and it faces a different type of challenge and different type of architectures one can think of. Here, what you're seeing is actually a very large area, a film or single monolayer of molybdenum sulfide layer wrapping a silicon step. And you can already see the kind of challenges that you might find in this type of materials. As you put this on a substrate, you can see defects like blisters or wrinkles, edges, And all these have kind of a significant impact in the actual properties of these nanomaterials. And again, this is another aspect that I would like to say, that most of these synthesis techniques that we use today to build nanostructures, they end up with materials that have an intrinsic variability in structure as well as dimensions and defects. So controlling all these different aspects would be ultimately very important if these materials are going to be used in nanotechnology and systematically to develop applications. Now, 2D materials are interesting, and there have been many exciting examples of why these could be of interest. From a materials point of view, a lot of people have talked about what happens when you start putting these together, these atomic layers, in various order, in a combinatorial way. Can you take layers from different compositions, put them together, and what kind of materials would you get? What kind of interactions would you expect? Change the electronic structure of these materials as you choose and build stacks of various layers of different compositions. Now, again, to talk about challenges, these type of atomically thin layers could be extremely sensitive to the substrate on which they are placed or the medium in which they are placed. This is a specific example of an experiment we did a few years ago, where these structures were placed on a pre-patterned substrate of silicon. And depending on the strain that was induced in different locations of these 2D materials, the electronic structure changed. So although molybdenum sulfide layer is semiconducting, the areas where there was high strain, particularly the tip of these features in the substrate, it became more metallic. So one thing that is obvious is that it's very important to consider what kind of substrates you would use for devices based on these type of structures, and how difficult it will be to create repeatable architectures and consistent devices based on these, particularly because of these strong interactions that can result in changes in electronic. There are also some very curious things about these type of 2D layers. Because of the atomic thickness, there's been talk about transparency. Of course, many of these are optically transparent, but going beyond just the optical transparency, people have also been noticing that they could be transparent in many other situations. So, for example, we did a lot of work on looking at a very, very thin coating of a monolayer of these materials like graphene, and see how they impact as an interface layer in the physical properties of the substrate. So it was shown that the wetting property of a substrate will not be affected if you put a thin layer of graphene on top of the substrate. So there's some kind of a transparency that is happening, and this is probably due to some electronic effects. And here is another example where we showed that the catalytic activity of typical catalyst, metal oxide catalysts, are not affected if you cover them with a thin layer of graphene. There seems to be some kind of electronic transfer that is occurring through the intermediate layer of graphene. So there are many examples that allow you to take advantage of the extreme thinness of some of them. And there's a large family of these structures now available that people have made by various techniques that we can play around with. Again, as a material scientist, this is really an expanding area because there are different compositions and different electronic structure of materials that are available in this 2D format. And there are also some long-standing interest from the device perspective. Again, this is just an example of the work done from UCSB in collaboration with us on devising a new type of tunnel FETs. Again, as you scale down the size of the channel in semiconductor devices, face lots of problems, electrostatics being one of them, or this swing, which is the thermodynamic limitation in how the voltage scales to the dimensions. And typical scaling down of the traditional semiconductor materials does not really allow you to cross this barrier, but it has been shown that using 2D materials, which are very specific in terms of surface dangling bonds and so on, one can surmount some of these barriers. So again, there's, from a device perspective, there's also quite a bit of interest. So it's important for us to see how we can tailor these materials and create good quality materials and create architecture that would be useful. How do you make some of these materials? Again, we have done a lot of work in this area. One of the ways of doing this would be simply exfoliation. And if you remember, the early work on graphene was mostly about physical exfoliation of graphite, but it can be now transferred into a large area, large scale liquid phase exfoliation. And there are many, many examples now available. Exfoliate these 2D materials from van der Waals structures or non-van der Waals structures. And you can create 2D materials for different crystallographic orientations by cleaving in layers from bulk as well as van der Waals structures. Another approach to create these materials would be chemical vapor deposition. And again, many groups have shown that a large library of various types of 2D materials can be grown. Again, large area growth, roll-to-roll manufacturing in some cases, going all the way from graphene to insulating to semiconductor materials, its deposition technique. And we were, in fact, one of the pioneers in this area, particularly in the TMDs, the transition metal chalcogenides. Using metal oxide seeds, we were able to show that you can reduce these into chalcogens, by chalcogens into TMDs over quite large areas. There are also some very unique ways of creating 2D materials. This is another recent example. This is from a group in Beihang University, collaborating with us, trying to see how some of the 3D structures could be transformed into 2D architectures. Particularly from starting with this Maxine phases, they were able to show that by interaction with chalcogen vapors or hydrogen chalcogen vapors, they were able to create high quality doped intrinsic 2D materials by this topological transformation. And so that, again, what I'm trying to say is that there are multiple pathways that you can build 2D structures, and that allows you to really think about how you can assemble them and structures that would be of interest. Now, one thing to think about also is that defects could be of importance in these materials. Many times when you're growing atomically thin layers using vapor phase deposition, you are going to end up with lots of different types of defects, grain boundaries, point defects, all kinds of defects. And the question that has not been very clearly answered is how do these defects impact the properties of these materials, electronic, optical, and so on. Here are some examples of different types of defects that you find. Grain boundaries have these topological defects, which has been seen both in graphene-like material or TMDs. So one has to think about what the impact of these defects could be in the ultimate properties that we find. Here is an example of that from the Columbia group. Again, this is not from our group, but they kind of clearly show that defects certainly impact the ultimate electronic structure of these materials. So two different techniques used to grow the same material, and in the PL spectrum, you can clearly see that one has some better properties, very nice, very tight, photoluminescence line width that shows intrinsically close to the theoretical material, and there are materials that can have defects which does not conform to this predicted structure. So one of the reasons why you're finding a range of data from many of these materials grown in different places and different groups is partly because of the defect densities that these materials. Now, one other opportunity is also to grow very large crystals, and again, that's something that has been done in many groups now. People can grow large area using many techniques, all the way from simple thermal CVD to MOCVD. And also some of the grain sizes that you can get goes into the millimeter scale. So almost like single crystals, people can grow. And it's important to do experiments with these type of materials to see consistency. And that's things that we have been also looking at. Now, ultimately, when it comes to assembly and the nano engineering aspect of 2D materials, what we are really interested in is creating these artificially take these atomic layers of different compositions and put them together in different ways, create stacks of different heterogeneous architectures, and see what the properties of these materials are. Again, that's really a great playground for material scientists, and this is something that we have been quite interested in. Now, the simplest way to do something like this would be through solution assembly. One can think of exfoliating materials of different composition and mixing them and then solidifying them to make artificially stacked. Of course, this does not really end up with ordered stacks unless you create very specific chemistries between interfaces. Most of the time, you end up with a random distribution of these layers in these stacks. Even those could be quite interesting, but again, the long-term goal would be to create these periodic structures that where the properties could be predicted. And one way to do this would be using vapor phase deposition. You can grow materials layer by layer, and again, that could lead to the periodic 2D stacks that one would be interested in looking at. But they also has limitations. For example, in order to build up a thick stack, it would take quite a bit of an effort and time, and that's oftentimes not really feasible from a practical point of view. Intrinsically speaking, this could also be challenging because there are different faces to these materials. The orientations could be challenging. So from a growth point of view, the question is, how do you controllably build some of these stacks from materials of different compositions? And in our group, we have done work over the years to see if you can find the right window in which some of these ordered stacks could be grown. Here is an example of a more WS2 type of material where the vertical stacks have certain type of orientation. There is another complication, which we also found that at the lower temperatures or under certain conditions, these materials could also grow side by side, which means that one could, in addition to having these vertical stacks, especially when you're growing them together, they could also create lateral interfaces or lateral heterostructures. So if you were to really build an artificially stacked, layer separated structure, it could be quite challenging. You need to find exactly the right window in which the formation of these stacks occur compared to the lateral heterostructure. But you can find these, specific windows. We, under certain conditions, we were able to create this 2H stacking of the tungsten sulfide and molybdenum sulfide, and also for other systems like selenide. So I think it is possible, but it could be quite challenging. And again, this goes back to the same issue that we have for the synthesis of many different nanostructures. The intrinsic variability that the system would exhibit is too large to really control the specific formation of the specific ordered architectures. And the long-term question would be, how do you deal with this? How can you really think about utilizing these randomness that will be present in any of the manufacturing technique that you would use to make these materials. Now, I mentioned about the lateral infrastructure. They could also be quite interesting. Here is a perfect atomically sharp interface that you saw. And one could think about creating some of these materials for device applications, especially if you can control the domains in this lateral structure. One thing that I also will mention later on is the stability aspect of these interfaces. If you have an atomically thin interfaces, diffusion and other physical phenomena becomes dominant, and the question is how stable are these interfaces in a 2D system. Now, there is another aspect to this which has also become quite fascinating, and that is this whole idea of twisted layers. People call this twistronics. Essentially, the question is, can you create this periodic potential within layers that are stacked on top of each other and create moire patterns and change the electronic interaction by doing this type of twisting? Can you control, for example, the exciton binding energy and so on when you have these twisted bilayers? That's a great perspective and idea for devices, but from a material point of view, the question is really how viable this could be. I mean, how stable these kind of structures could be, particularly if you want a large area twisted bilayers or multiple layers. Then you need to have single crystals of each of these layers, and also you need to lock in a specific type of orientation. And how do you really do that? And again, it's a lot of trial and error many times, and people have been able to do this. And also, what kind of tools can you use to quickly look at these orientation differences in these layers? We recently published a paper suggesting that you can use electron energy loss spectroscopy to look at the various types of excitons when you have these twisted bilayers. And again, I mean, this could be all fascinating from an electronic point of view, but materials perspective, it could be quite challenging at the same time. Now, the chemical modifications I mentioned when I talked about the nanotubes and other carbon structures, this could also be very interesting for 2D materials. Because if you add functionalities on individual layers, that changes the whole picture of interactions between layers as you stack them. On the other hand, one can change the amount of functionalities that you can put in on these 2D layers and create interesting devices. So here is a simple example of a graphene oxide film that has been converted into reduced graphene oxide using a laser beam to build an in-plane supercapacitor devices. And again, this is a combination of bottom-up and top-down approach to creating two-dimensional material-based device architectures. And such processing could ultimately lead to some really unique type of devices in both graphene-based systems and other systems. Now, many of the chemistries that you implement on these type of materials changes the actual topology of the system. So if I take a graphene layer and functionalize this with, let's say, oxygen, it is going to change the hybridization from sp2 to sp3. So that actually breaks up the lattice of the topology of the system. Now, there are also ways of mild chemistries or chemical modifications. This is a Lewis acid-base kind of an approach where we were able to do surface complexation and change N-type to P-type, electronic structure on some of the 2D materials. This particular example is for indium selenide. But what I'm again attempting to say is that in 2D materials, you can have either very strong chemical modifications which changes the topology, or mild chemical modification that keeps the topology as 2D. There is another approach that has been used traditionally in graphitic systems, and that would be intercalation, and intercalating elements into the galleries or into the interlayer space that is available in many of the 2D systems can change the properties quite significantly. And that's a huge amount of work in graphite intercalation. We are also starting to see work coming out in intercalating 2D systems like TMDs and so on. And ultimately, the design of such materials would be fascinating. Can you create a multiply stacked system with different compositional layers, with different type of intercalants, so that you can really have a whole tunability in terms of electronic structure? Or utilization of these ligands that I mentioned in terms of the cluster assemblies. Can you also create different types of molecular interfaces between 2D layers and substrates, or between two different 2D layers, and change the electronic properties? So there is a lot of possible interfacial chemistry that one can think about in modifying or tuning the electronic structure of this type of 2D materials. And in addition to that, you also the structural alterations you can do in terms of twisting and other kind of. Now, let me also mention this whole idea of phase diagram approach in creating interesting 2D materials. And I'll give you two examples. One is this boron nitrogen carbon system, which is a really fascinating phase diagram that shows an entire range of possible compositions. And we have been very interested in this phase diagram. We already know that materials like carbon and boron nitride has been very, very useful. But when you look at these three component systems with boron, nitrogen, and carbon, we have seen that there are some issues of creating these thermodynamic phases of B and C. Most of the time what happens is that you form these segregated domains of graphene and boron nitride. And the good thing is that you can envision some of these engineered structures with graphene and boron nitride side by side in a lateral heterostructure. And one can building interesting devices like antennas and so on, all in 2D. And many such structures can be made using this engineering, 2D engineering approach. Hexagonal boronite, itself is a very fascinating material. Not talk too much about the applications of some of these materials, but recently there's been some promising applications of hexagonal boron. It's a high temperature, very unreactive type of material. And today one could grow very thin films of these materials. They're extremely strong, tough, oxidation resistant. Here is an example of a nano coating that withstands oxidation. They're corrosion resistant. So again, it's some sort of a nano engineering where you are controlling the number of layers and controlling the defect densities in these materials as you deposit them on different substrates. There's also been examples, very recent work, showing that they could be extremely good thermal conductors in applications like electrothermal desalination, and also protects the metals on which they are coated from corrosion. So again, engineering of these materials, these 2D layers on substrates can ultimately lead to some very, very important applications. And again, boron nitride is also a material that you can think about functionalizing, although much more difficult than graphene. And we have,
Professor Ajayan, please keep close to your microphone. That's not very
okay. All right. So I will. How much time do I have left?
That's okay. Just a few seconds.
Oh, okay. So I'll finish it in a few minutes.
No problem. You have 8 minutes.
Okay. Okay. So what I was trying to say is that functionalizing 2D materials also gives you an opportunity to change electronic structure, physical properties. We have been looking at fluorinating a lot of materials like boron nitride, and that gives you an additional leverage to alter properties. Another example is molybdenum telluride. Again, a different type of 2D system, a TMD system, reasonably low band gap, and it comes in two different phases, 2H and the 1T prime phase, and the semiconducting and metallic phase. And there's a lot of work that has been directed towards controlling what phase you can grow. We have done some work in this area, and if you look at the growth of these materials using CVD, what you end up seeing is that you get a mixture of both the phases under normal. So you can make a nice film, but it will have these 2H domains and the 1T prime domain, semiconducting and metallic domains. And the question has been, how can you controllably do this? Just like I showed in the case of graphene and boronite, which of course has a segregation tendency. How do you really control the domain formation and the domain distribution in these systems? Ultimately, it would be a great idea to have a metallic phase which can be contacted and a semiconducting phase as a channel. And that has been our goal. And there's been a lot of work in literature that shows how you can do this phase patterning. By radiation or by strain engineering, people have shown that you can create these localized domain formation, H and 1T prime. One thing that we have done recently is that by doping this molybdenum telluride with tungsten, you can change from the semiconducting phase to the metallic phase. So by locally doping these type of layers, we were able to create this periodic 1T prime and 2H phase. The 1T prime is where the tungsten is doped. The other area of molybdenum telluride remains as 2H. So there are some tricks you can play to get phase engineered architectures within the 2D. And the final piece that I want to mention is about this this doping, or going from two components to higher components. And again, this is a phase diagram approach. People have done some work, but not too much in terms of understanding the phase stabilities of many of these phases in 2D materials or TMDs. So as you go from molybdenum sulfide to a three-component system by adding either the chalcogens or the metals, you start seeing a pretty uniform doping in these lattices. Unlike the boron carbon nitrogen system, here you can see that there is quite a bit of uniformity in the way the dopants are distributed. And by continuous doping, you can actually change the band structure to a large extent. You can change the band gap of these materials. But we have also done some theoretical studies that shows that this band gap tuning can be enhanced as you go from the two-component system to, so you go from binary to a quaternary phase system, you can have a better band gap tunability by changing the concentrations of each of these. So I think it's important for us to really understand how the phase diagram works for many of these systems if you want to have better tunability in these 2D. And ultimately, we have been able to create these 2D alloys of 3-component and 4-component systems. But of course, it is also challenging because in many of these systems, the phase stability could be of interest. As you change conditions like temperature, one can go from a fully random alloy to a completely segregated heterostructure. So when we are dealing with 2D materials so thin and small, at the nanoscale, one has to consider how the stability of these phases are, especially for long-term applications. And this is true for all kinds of nanostructures. How stable they are in terms of phase stability. As you change conditions, temperature, pressure, pH, how do you change? How does the structure change, and how does the electronic structure change? So here is a good example of a randomly distributed 4-component alloy that contains molybdenum tungsten. Some of these materials are now being explored for catalysis and things like that, but very little overall has been done in really understanding phase stability. Here is a very, very interesting example of this 4-component system where as you heat, you change this completely random alloy to a fully segregated and tungsten selenide system. So again, from an engineering perspective, it's extremely important to understand things like phase stability, compositional stability, diffusion of atoms within these 2D systems. And if I start to put stacks of different layers with different compositions, then even the three-dimensional diffusion becomes quite important. Can these layers with different atomic compositions mix together? So there are lots of questions that are still unanswered, and these might not only lead to better understanding, but also the ability to tune these structures from the perspective of composition, phases, domains, and so on. So maybe this is a good place to stop. I had a few more slides that talks about nanostructuring. For example, you can take these graphene layers and build quantum dots from them, or nano ribbons from them that allows you to create interesting architectures with different properties. But again, that's probably for another talk, but let me kind of stop here and say that many of the things that we do as material scientists are optimization of material systems, phases of defects, structures, and the question is really how does stable systems evolve, and how do you make sure that they are stable over long periods of time? Particularly for nanomaterials, there are significant challenges from an intrinsic point of view. Many of the manufacturing techniques that we use today does not allow you to create size-selected, specific type of architectures in large volumes. So there is this intrinsic variability that you have to deal with. And secondly, and as you start to put things together, certain significant, bottlenecks arise, interfaces. How do I, if I put two materials together, or even two nanotubes together, for example, how does the interface look like, right? I mean, individual nanostructures might have specific properties, but as you build larger structures, engineered structures, then you start seeing the compromise at every step of the way. So I think nanotechnology, in my mind, or nanoengineering, is still in its infancy, and the kind of approaches that we are taking to build larger structures, there's still a long way to go. The question is, do we want to emulate the naturally occurring systems or biological systems which have done an amazing job of building architectures from bottom up? But that would give us a different type of architecture. Many times they are not as periodic as one would expect or what one would want, or they are probably not as densely packed as one would expect. So it oftentimes, probably in the long run, is going to be a compromise on what kind of architectures we want, what is the right pathway towards getting to that point, and how do you really optimize the structural property relationships. So thank you very much. I would like to quickly acknowledge a lot of people. And again, these have been examples taken from various stages of our work in the last several decades. And for all the group members that contributed. Thank you.
Thank you, Professor Ajayan. That's a really, really wonderful talk. Yeah, it's really rich information. Yeah, so we do have several questions come out here. Then first we go to the questions part. Okay, first question is available from LSU. Professor Ajayan, thanks for your wonderful talk. About PhD students working on the solar cell, can you comment on the future of a carbon nanotube or other nanomaterials in this field? Or I should shift the topic to other materials. I think it's fresh.
I mean, I certainly wouldn't shift topic because these are all exciting materials from a fundamental perspective. As a PhD student, I think you should be more interested in looking deeply into the basic aspects of some of these materials. The case of nanotube is an interesting one. I think over time, the biggest effort has been in trying to identify specific type of nanotubes with chirality so that you can access the semiconducting properties of nanotubes. So, or metallic properties. So I think we have reached a point where there has been significant developments in isolating specific type of nanotubes, semiconducting metallic. So perhaps it's a good time in terms of looking at some of these materials for applications like solar cells, or transparent conducting films, or things like that. So I don't think you should think about changing a topic because CNTs are quite challenging. What I would do is to maybe find the right kind of material, collaborate with the right kind of people who can provide you with the specific type of nanotubes that makes your life much easier.
Okay, yeah, this actually, I saw this question. I think about last year, one Professor Yan Li from Peking University. Yeah,
Right,
she is doing very great job in CNT. Then that time he already say one word is many people tell me I should change the field, but I choose to stay on this because I found that still a lot of problems, a lot of questions I should answer. Then Professor Yan Li now is a superstar in this field. I think maybe following your answers to these students is keep on going, right? You even can
I think so, right?
Yeah.
I mean, many times these fields take a long time to kind of stabilize. And one of the, I've been in this field for nanotubes for a long time, and the early times were all dedicated to understanding individual nanotube properties. But I think purification and selection of the right electronic property nanotubes have taken a while. But it's I think in a good position right now, as I can see.
Okay, great. Yeah, so the next question is Lily from Xi'an. Thank you very much for your great talk. As you mentioned, 2D materials now is a very hot topic, and it has super characteristics and potential applications. But most of them are fabricated with chemical method, and it's hard to merge it with a real 3D function devices. Any suggestions?
Yeah. So this is exactly what I was kind of trying to convey, that, there are many ways of making 2D materials, and many of the properties that we really want to see will be related closely to the quality of materials and the way you create them. Once again, I think there are well-known 2D materials that have become quite, quite advanced in terms of synthesis technique. I mean, people have been using more control techniques like MOCVD to get very good quality, large area, single crystal type of materials. So I think, again, it's an evolving field in from my perspective. The quality of materials are getting better. And, I don't think it's only the chemistries that have been used to create good quality materials. I think people are looking at industrial type of deposition methods to make these structures. And, it's always, there's a time lag between, what we do in the lab and what ultimately, is adopted by industry. And I think materials like TMDs, now there's quite a bit of interest from the industry side. And I think there's been push towards making systems that are more robust and higher quality. But it's a good question. I think, again, it's not just about 3D materials, but in general for nanomaterials, right? The quality of materials really is a key for many of the applications to come through.
Yes, that's also one of my questions to you is because I was working in the MEMS field, microelectronics, mechanical systems. So this normally fabricated a lot things by the mass production. So now if we want to, use the functional 2D materials, it's kind of a really challenging.
Yes. Yeah, I mean, especially for devices and, electronics, you probably want very pure, very controllable type of structures. right? If you're talking about some applications, that do not need that. For example, let's say you're using this material for catalysis. Maybe are actually useful, right? I mean, so I think it depends on the application you're looking at, and the quality of material is strongly correlated to the application that you're looking at.
Okay, really great. So yeah, now we can move to our panel discussion part, because today we have a really strong panelist, Nick Fang. Yeah, Nick was a professor in MIT. Is also a superstar, for the nano materials, metal materials. So today Max has a lot of questions for the panel discussions. And we also have a young star as Meiqi Li, was from Peking University Physics School. So he's a superstar in, 2 weeks ago. He won the title for the, PhD students competition. So yeah, now let's welcome 2 of them to join our panel discussion. Yeah, please. Okay, first we can start with Meiqi. Yeah, hi, Meiqi. So you are challenges, I can hear you. And so as our challengers, always has, opportunity to ask the questions first. So please go ahead.
Okay, thank you, Professor Alice, and thank you, Professor Ajayan, for your wonderful report. Although we are in a very different field, I'm very impressed by the development of those fascinating nanomaterials. The development of nanomaterials has also promoted the development of biomedicine and bioimaging. So I'm interested in the impact of carbon nanotubes and graphene materials in the field of bioimaging and biomedical. Can you talk more about this?
Well, I mean, bio-related fields are not exactly my expertise, but things like graphene could be very, very interesting. It has already been used as supports for imaging techniques because they are so thin and pretty strong. But I think there are other potential for 2D materials in general, not entirely for nanotubes or graphene. There have been attempts, at least that I know of, where you can dope some of these materials with rare earths and things like that, which could provide good contrast in the case of bioimaging. I think the possibility of encapsulating, let's say, nanotubes with certain higher contrast materials could be very useful in bioimaging. I think, again, things like gadolinium has been used to get magnetic contrast. So I would consider these materials as, again, the basic units, which can be used to build the kind of structures that you want for better contrast in imaging. Right? And carbon may be a very interesting material because it's also biocompatible. Right? So maybe for some of the maybe MRI or maybe other types of imaging that you use, these could be the carriers. Obviously, to get better contrast, carbon is probably not the best element. It could be doped with some elements. I think we have done some work in rare earth doping, and that could be also of interest.
Okay, Nick, did you have any comments on this?
Well, I'm not familiar with the biosensing part, so maybe I should let Maggie talking about her questions.
Okay. Yeah.
Or comments.
Yeah, Maggie, please. Yeah.
Yes, thank you, Professor Ajayan. Thank you for your instructive answer. Recently, artificial intelligence has developed rapidly and has been well applied in many fields. A material with good performance normally requires a lot of screening and performance evaluation. This will be time-consuming. So my next question is: can artificial intelligence help in the development and the property prediction of nanomaterials?
It's a very important question, and I think a lot of people working in the area of not just nano materials, many material science areas look at this as a is a potential opportunity. One of the things that I was telling during my talk is, how do you really optimize a large number of possibilities, right? I mean, if you're trying to create a material for a specific applications, what are the different pathways you can take? What is the best combination of structures, particularly if you're thinking about complex, multi-component kind of systems. And AI could certainly help, or machine learning, to optimize certain systems, right? I mean, it's not easy, certainly from an experimental point of view, for a synthesis point of view, to do large number of experiments and optimize. So I think machine learning could, as you said, could be certainly a screening approach, and it may not be only machine learning. We have been working with the theorists and modeling folks for a very long time to really get a better handle on how, what direction you want to take in terms of material synthesis or optimization. And machine learning gives you an additional leverage to kind of maybe look at larger number of systems. And, I do not believe that AI or machine learning can solve all the problems in materials, discovery, but it certainly can help. And I think it's slowly going, beginning to happen. People who have been working with modeling folks are now also looking at collaborating with people with computer science expertise, so that you can actually look at a broader range of systems, so that you can optimize better. So again, it's probably a broad general answer, but that's certainly the trend that is happening in most fields, including materials and nanotechnology.
Yes, that's true. So Professor Ajayan, actually in your slides, you have mentioned one, Liu Zheng, from Singapore. He's doing 2D materials. As last year, he delivered talk on ICANX. He talked about, he use artificial intelligence, to help for his predictor of the structures of 2D materials. So that's really kind of a trend. A lot of people will, use this kind of tools to help. So Meiqi, did you have other questions? We give the chance to Nick. Okay, Nick, please.
All right, so that's a wonderful talk. Thank you very much, Pulickal. My question for you, when I was listening to your phase diagram of 2D materials and other alloys, it makes me think about, for example, the boom of metallurgical studies. At that time, I think we use a lot of examples of industrial research, industrial case studies to motivate our students. This is the reason that material science was actually critical, and pursuing such a fundamental study is a win-win situation. In terms of 2D materials, what is your view or position of the partnership between academia and the industry?
I think it's a very interesting question, and everybody thinks about this. Again, not specifically for 2D materials, but we have thought about this for nanotubes and graphene. Of course, my position is that we should have stronger ties with industry and academia. There are countries that probably have this much better. For example, I worked in Japan, and there seems to be a stronger relationship between industry and academia there. One of the things that I have always felt is that in academia, we have a lot of freedom to look at all kinds of things, right? I mean, it's a much broader perspective that we have. That has got advantages and disadvantages, right? I mean, advantages that we have the ability to discover and innovate and so on. But at the same time, we often miss important questions and problems, right? Even in the case of 2D materials, what would be the most, the easiest thing that we would want to do in academia? Explore more number of materials, perhaps, right? I mean, fundamentally understand maybe the growth techniques for different types of material. But the question really is, if you have n number of materials, how do you really, zoom in on one that is really important for an application? Mm-hmm. So I think it's always a compromise between the breadth and what is really practically useful and feasible. Right? So I think the moment you start working with industry, you start realizing that there are certain specific things that you want to focus on if this still were to go into application. Let's say that you're going to look at a particular 2D material for electronic applications. I mean, today we grow these materials at 1,000 degrees or close to 1,000 degrees, right? That's really not going to work, right? If you were to kind of directly deposit onto a substrate that is of interest for semiconductor industry. Or, many times we grow these materials on a substrate and transfer them to another substrate. I mean, that's not really a feasible approach, right? So there are many aspects that we should be thinking really upfront before we start embarking on some of these wonderful ideas. So I think it's extremely important. I mean, may not be always necessary for the industry to deeply get involved in the research that we do in academia, but I think it's good to get their viewpoint and their problems and their, the long-term solutions that they are thinking about. What is the next generation of devices they want to build, and how does the 2D materials come into that kind of a platform? What options do we have, right? So I think this dialogue is very important. So I think it's a delicate balance, and I've been on both sides of the fence. We have quite a lot of support from industry. May not be for the 2D materials area, but in other areas. So the perspective is quite different. And I think, especially for students, I think it's very important to have these both perspectives. So, I mean, in my group, we encourage most of the students to at least spend a little bit of time in industry during their PhD so that they see what is relevant. I think academic life is wonderful, and we can think about lots of things, think out of the box. But end of the day, if practical applications needs to happen, I think we need to see the viewpoint of industry. We need some kind of directions on where we should go.
Actually, this dialogue now is very hard in mainland China, because most of the students, asking questions about what do we do now? Yeah, can it be really come true? It's Sunday, So even for a lot of people was asking this to the scientists, what are you doing every day? Nothing come out. Right, nothing can in the real applications. But I mean, Professor Ajayan was answered the question in the interview. As a scientist, mostly you should interest in the, the funding of science, right? The fundamental things. Then you get out some techniques and some fundings. And then eventually they will come out to be some product. Maybe not all of them.
I think academic perspective has always been a long-term. Basic sciences, but maybe that is changing slightly, particularly with pressure on funding and things like that. There is obviously a movement towards looking at things that are more application oriented. I don't totally agree with that, but I think it's very important that this whole change has at least brought in the idea that it's important to look at the right problems. It is important to at least see what the real problems are, what industry is looking for, right? I think we still need the breadth and the freedom to think about broader ideas, because that's the only way, very new things can come out. and innovations can happen. But it's good to know what the reality of the situation is, right? So I think it's a very delicate balance in my mind.
Okay, great. So Nick, any further questions?
Yeah, I'd like to follow up on this thought-provoking discussion. I would say like 30 years ago or 40 years ago, when we were talking about the industry, talking about semiconductors, we send our students to IBM, to HP, to Bell Labs or so. But today, there is a significant constraints. For example, say sending students who are interested in more of a, I would say like long-term research to industry. I think that's more of a, so to speak, a constraint. I don't know. Would that apply to your students as well, Pulickal?
It depends on the industry. I mean, we have had certainly luck with our students finding positions in industry and also finding internships and so on. But I totally agree with you, Nick. I mean, we need to build these ecosystems where, there is a dialogue between industry and academia, because at the end of the day, academia produces talented students who are trained with various capabilities, and industry wants a workforce that is modern, right? I mean, it's not a one-way thing. I mean, they need us as much as we need them in some sense, right? But I think it's a wonderful discussion, and I think with time will tell how far we go on this. But I think it's important for everyone to kind of bring in this dialogue into the classrooms and into the groups to see, to at least have, this ongoing dialogue on what industry is really looking for. I mean, we are working on 2D materials. Yes, I mean, it can be an open-ended questions and we can go in all different directions. But I think if you can introduce this dialogue on what might be the industry looking for, and why, what is it that we can actually do to at least put some constraints on this, totally open-ended research that we do, to enable them, to help them. And, that way, there will be a better connection between the two sides of the coin.
Yes, you give me one idea. Maybe next time I can ask. I should invite the industry people to join the panel discussion.
Yes,
then,
yes.
That will help us a lot, because we can provide so many rich information of the latest results, right? The science and technology. Then they come in, say what they want, what are they really looking for. Yeah, that will be a building bridge. Yeah. So
I mean,
that's our time.
In my mind, the students, the young people who are going to their PhD or any other program, there are two things, right? They need to know and think about. One is that this time during their PhD is the best time for them to kind of expand their horizons, think broad, think out of the box. But slowly, I think this piece needs to be added to another aspect, which is, what can I do for society? How can I do this for the society, right? And industry and applications come as part of this bigger responsibility. So I think so far we haven't really concentrated on this, in our curriculum, in our training programs. I think it's important to bring that aspect in, and that automatically will bring in this aspect of applications in industry. At the end of the day, we do this, whether it is short term or long term, has to be useful in some sense, right? I mean,
yes, yeah. Okay, now deal. Next time I will invite them. So Nick, so Ajayan, I will invite both of you to join the discussions. We invited the industry people, to discuss for what we can do for the society. Yeah. So Weiqi, I give you a last chance to ask questions.
Thank you, Professor Alice. Okay, Professor Ajayan, you have made such an outstanding achievement in the field of nanomaterials. I'm just curious about the motivation that keeps you doing research. And can you share some advice to the young scientists?
Yeah, motivation. Yes, I think it's again something that what everybody has to bear in mind, that we are all motivated because science is such an exciting thing, which is logical, which produces some unknowns. Exploration of the unknown is what drives us, right? I mean, I think all of us are interested in solving puzzles, and the curiosity is what really drives our intellect. And it has always been a pleasure for me, because you're surrounded all the time with young people who are ready to think and explore. I think in the interview I mentioned that one of the things that I really love to do is to travel and explore. And this is essentially a travel and explore from an intellectual point of view. I think there are many things. I think I feel really fortunate to be in science and technology, because we are really trying to understand how the world works and how it can change. So our profession brings in change, and I think that's a great thing to be in. So yes, I mean, sustaining motivation is not easy, but I think if you are focused on the basic elements of this whole thing, which is exploration and curiosity-driven approach, then I think it is sustainable. I've heard many times that people get burned out, but I think that's because you kind of tend to focus on the wrong things. Just focus on the beauty of what we can do and how we can change the world, and the puzzles that we solve and the things that we can explore. So make it simple and keep your focus.
Leichi, that's okay for you? Yeah, I think that's the best answer for you, because now you are PhD almost in the last year. So it looks like you're going to burn yourself. So yeah, if go further and then stick with what you love. Yeah. Okay. I think you're born as a scientist. You just go ahead.
Yeah.
Okay. Great. Thank you very much. Thanks all of you. Time flies. Now we almost came to the end. So Professor Ajayan, yeah, we have this certification for you. Yeah, this was an electrical one. Next time I met you, I will give you a real one. Yeah. So as this was a ICANX, tradition, we deliver everyone this beautiful, certification. Thank you very much.
Thank you very much. Thank you, and take care.
Yeah, okay.
Nice meeting you, Nick.
Nice meeting you. And almost to the end of the talk. And today I have a lot of things to announce, because next week will be a big week for us. We will kick out this ICANX story as our new program, and every Thursday. So from 8 o'clock in the evening to 9 o'clock. So that's 1 hour program. This program is like what we heard in the front of this talk. So this was an interview, before the ICANX talks. We interview all the speakers and talk about their stories. So next week will be our official launch, the ceremony for this ICANX story. So on the stage will be Professor Joan Mary Lin as a Nobel laureate, in chemistry. So our moderator will be Hui Wang, as Catherine. Her interview is very interesting and share a lot of stories about the scientists and their fundamental and how they founded all this kind of science. Yeah, what about their life? So will be a lot of interesting stories. The slogan of this ICANX story program is meet, must, and share wisdom. So yeah, you will enjoy this next week, since next Thursday. So 8 o'clock, yeah, continue with us on ICANX. So after the ICANX story, more about the speakers,
you are listening to the talks. So next week, Friday talks is Professor Lin. He's going to talk about the perspective in chemistry. Yeah, for the silver, chemistry to the adaptive chemistry. So we have a big team for this. Discussions and a lot of questions. Welcome you join us next week and Friday. And after talk, we have this new journal launch. It's about E-Light. So we have two, editor-in-chief will join us to talk about this E-Light. This will start at 9:30 next Friday. And I have a few conferences to announce because we locked down a lot of time. So this summer we'll have many conferences. This conference will be in Xi'an. It's focused on the vibration and energy harvesting applications. So it's July 9 to 12. It's a call for the papers. So please submit your papers if you are in this field. And we have this flexible electronics conference already 6 years, and this will be the seventh time. So in Wuhan, so Huazhong University of Science and Technology is my university. I was graduated there 20 years ago. So welcome, to come to my home university at UST. So that's a really beautiful place and a beautiful conference. Enjoy that. And we have a contest was coming on. This will be in Beijing. That's a really beautiful, contest for the startup companies. So please take a look at this haiku contest. And we have ICANN contest is going on for the college students. So if you are interested, you're welcome to visit the website, and there are a lot of information for the students. And that's all for today. I see you next week. Thank you very much. See you.
Thank you.